Okay, let's start. Good morning. Today I'm going to start taking attendance. So here's the attendance sheet. Last name, first name, and then signature. Fairly straightforward. Start here. So regarding problem sets, so I started looking into the feedback for problem set 1. I think I'm going to spend more time later this week, maybe next week. Some of you are concerned, and rightfully so, I would presume. But I just want to make sure that we're on the same page regarding many things, regarding grades and stuff like that. Just for now, though, I would like to say something along the lines of the following. So, and this I see in your responses as well. This class, it's kind of hard to teach, not only because of the content, but also because many people who are taking this class, they come from different places and they are going to go to different places. And so when you have sort of like a heterogeneous audience, it's hard to sort of figure out how to exactly give a class like this. And so the way I handle things like this is that I make sure that it's as open-ended as possible. So there is a lot of room for growth. But at the same time, the people who are mostly interested in taking this class for the purposes of graduation, they are not victimized, right? So the way this happens, I try to sort of balance these two situations is by being as lenient as possible when it comes to grading. And I hope toward the end of this week, once you see your grades for problem set 1, you're going to start believing me more. So being lenient in terms of grades, but at the same time, having a lot of material so that people who end up, people who are going to go to grad school, for instance, they're also not victimized by the lack of content, let's say, or sophistication. We'll talk about that more later. And so this week and next week, we're going to talk about a different type of structure. So far, we were talking about linear spaces, and then norms and inner products and things like this. This week and next week, we're going to talk about related, but in a sense, more flexible structures around the notion of distances. Yes?
Sorry, just going back. Will you be publishing like an answer key to problem set 1?
Yeah, so typically what's going to happen is that all but one problem or two problems from any problem set is going to be graded for completion. So that's going to be graded by the grader. One problem, which is going to be sort of, it's going to be a secret. It's going to be graded for accuracy, and that I'm going to grade for accuracy by myself. And the problem or the problems I grade for accuracy, I'm also going to write sort of as complete a solution as possible, and I'm going to submit it. Okay. So it's going to be on Canvas by the end of this week. And then, of course, yeah. Say again?
There's one or two parts I didn't really understand. I was hoping there would be like...
It's not going to be a complete solution. Yes, it's not going to be 100%. Because in a sense, like there's a lot of material in this class and the way I teach this class also. But at the end of the day, I have very specific things. So there are the main quests, if you want. So I want to emphasize those. And so when it comes to problem sets, for instance, the problem that I grade for accuracy is going to hopefully be the one that I hope in your head is going to be the main quest. Once you realize, oh, maybe you didn't realize it at the time, but this was the main thing. And then, of course, ultimately, that's also going to be quite possibly on the midterm, for instance. Like I'm not going to put problems that I haven't graded for accuracy on the midterm so that there are no sort of mysteries or surprises in the midterm. That's sort of like my style, a little bit. Yeah. We'll talk about the midterm design as well. And I mentioned this to a couple of you, and those of you who have taken 30-10 from me, you are familiar with this idea. So 90% of the exams are going to be non-surprising, and the remaining 10% or maybe 5% is going to be sort of completely bonkers. And so it's going to be fairly straightforward, let's say, to get 90%. very hard compared to that to get 95%, almost impossible to get 100%. I say this, but last semester in the final, 2 people out of 21 got 100% in the final, so I was surprised by that. But we'll talk about that later. Like I am not a big fan of sort of carrot and stick policies, so did that sort of answer the question?
Yeah, that makes sense why you do it that way.
Yeah. Any other questions, comments? Okay, so here's the important thing. So now we're going to start talking about metric spaces. Let's start with this definition. Let X be a set. Now I forget all about everything that I knew about vector spaces and whatever. This is an abstract set. A function delta, let's say, that takes 2 elements in this set and produces a real number, let's say, is said to satisfy the triangular inequality if, well, for any 3 points, delta of x comma z is dominated by delta of x comma y plus delta of y comma z. This is the mother of all inequalities in analysis. In anything, actually, as far as I'm concerned. But then again, I don't know much about non-metric things. And so I'm going to call D, again, I'm going to take a function like this. I'm going to call it a metric or a distance function on x if it satisfies a triangular inequality and 2 more properties that are more technical, I would say. So they're sort of like more negotiable. This triangular inequality is, in a sense, the non-negotiable property. If you don't have this, you're doomed, basically. If you don't have these other 2 properties that are more technical, you can still sort of fudge around and do things. And even if you didn't have this, you can still do things, but we're not going to get there. So a function now D and I want it to take non-negative values. I don't want negative values also. Is a metric or distance function on x if it satisfies the triangular inequality d of, let's say, x comma y is 0 if and only if x is equal to y. And d of x comma y equals d of y comma x. Okay. And so the second property is often called the point separation property. Of course, here you want to think of d of x comma y as the distance between x and y. And you're saying that the distance between 2 points is 0 if and only if those 2 points are actually the same point. And here, this is a symmetry property. It says that the distance from x to y should be the same as the distance from y to x. These properties should remind you of the axioms of a norm, and they are indeed related in the following sense. Let V be a vector space if this is a norm on V, then V of V1, V2, defined as the norm of their difference, is a metric. And this, so V1 minus V2, I can do this in a vector space. That's another vector. Then I take the norm of this. This is a metric. This is a very nice exercise. I'm going to leave it to you. So to sum up, we have now three structures, right? So at least on a vector space, we can define an inner product. And then an inner product immediately defines a norm. And then a norm defines a metric. OK? Any questions so far?
What does the TI mean?
Triangular inequality. OK. Let's see. Here's another example. Any set whatsoever can be considered to be a metric space using what is called the discrete metric. Let's let x to be, let's say, ABC. You have 3 points in your set. And so I can define the discrete metric on x to be like this. So x comma y. 1 if x is different than y, and 0 otherwise. This is what is called the discrete metric. You're saying, I have a bunch of points, and I'm declaring the distance between any 2 points to be 1 insofar as these 2 points are distinct. Otherwise, I have to choose the distance to be 0, because that's one of the axioms. Is the discrete metric. OK? And so how would I imagine this? Well, I have 3 points. And they sort of fit into an equilateral triangle, each of whose sides are 1. That's how I imagine this. Okay. If I had 4 points, I would need yet another point that's sort of like sticking out in a sense. And then if I had 75 billion points, again, in a sense, I would like to imagine something like that, but it becomes harder and harder, as you see. So here's another example, or maybe a definition. X be a metric space, Y be a subset of X. Well, let's say a metric subspace of X is a subset Y with the so-called induced metric. So if the metric on X is, let's say, D sub X, I'm just going to take this metric I have and I'm going to restrict it to points in Y. So this we define as this. So y1 and y2 are 2 points in the subspace, in the subset, but if y1 and y2 are elements in Y, they're also elements in X, which means that this still makes sense. So we can define it like so. Okay. Probably in the next problem set, which is going to be due after the first midterm, you're going to sort of see some ideas around this. But for instance, you can imagine the following situation. X is R2. And if I'm not going to say anything, of course, this has this inner product, dot product, which induces a norm, which is a so-called L2 norm, which itself induces a metric by this exercise that I erased, which is the L2 metric or the standard metric. So X, let's write it like this. P1, P2, that's 1 point. And then Q1, Q2, right? This is P1 minus Q1 square plus P2 minus Q2 square, and then square root. That's the standard distance, Euclidean distance. L2 distance. This is a distance you know from Calc 3. OK. Let's say that Y is this set, a unit circle. So how can I write this? I can say this is the collection of all those points, P and Q, such that P squared plus Q squared equals 1. OK? X is everything. Y is this circle. Okay. Now, if I were to take 2 points in Y, I'm saying, well, you can just look at the distance of these 2 points. Let's say these 2 points as points in X in the plane. Certainly, any point on the circle is on the plane. So I can just look at this length, the length of this line segment. OK, so this is what is called the induced metric. but there is going to be another metric that you may want to look into. You can say, well, in a sense, I want to think of this circle, this red shape, as a thing in and of itself. And so when I'm measuring the distances between 2 points, I don't want to leave the circle. And so you can say perhaps that instead of saying that the distance between these 2 points is the length of this green line, maybe it is the length of this arc. Okay, so this is, of course, a different distance, right? It's a different length. It still gives a metric somehow, but that is not the induced metric. That is what is called the intrinsic metric. Probably you're going to see some problems about this. In the third problem said, how do you even define it formally and so on. Pset 3. Okay. Any questions so far? Here's another example. Exercise, actually. I gave this, I think, in 3210, but let's repeat it here. So we're calling this in abstract a distance, but of course in practice it can model a bunch of different things. It can model something like, oh, you have one state, let's say x, or yeah, x, and then you want to switch to a different state, y, and the distance between them maybe is sort of the activation energy required to do that state transition, or it could be the cost of something, whatever. And so people really don't look just at one metric, but they look at multiple metrics. And given at the situation, maybe they change the metric a little bit. And there's this whole field called metric transforms. Okay? And in this field, there are all these statements like the following. If D is a metric, then so is lambda times D for lambda a positive number. Right? So for instance, in this situation, I called that the distance between any two distinct points is 1, but I could have just called it 5 too. Doesn't matter. That's another metric. You're scaling. You have your space, and like once you have the metric, you know how any 2 points are positioned next to each other. But when you sort of like change the lambda, maybe you want to sort of shrink things together. Another exercise is, if D is a metric, then so is D divided by 1 plus D. For instance, the benefit of this is the following. Your original distance, it's a very nice function generally, but maybe it is unbounded. For instance, the standard metric on the plane is unbounded. Right? But if you switch to this, well, the numerator is always less than the denominator, so this is a bounded metric now. So maybe whatever you're trying to do really requires you to have your metric to be bounded. So then you switch to this guy. And somehow, in a sense, this metric is equivalent to this too. And so you're not losing a lot of structure. There's a bunch of things like this, but these two I think are sufficient. Okay. Any questions? Let's see. Okay, I guess you want to start talking about sequences. It also turns out that once you have a distance, you can pretty much do anything you learned in 3210 using distances, epsilons and deltas and stuff. And this is why I'm introducing these as well. Oh, maybe here's another exercise. Let's do like so. And take x to be the oh, okay. Riemann integrable functions defined on the unit interval. I'm going to consider this with the C0 metric or supremum metric. So d of fg, I'm going to say, is the same thing as sup of f of x minus g of x in absolute value, where x varies between 0 and 1. So this comes from the C0 norm, you see, and by the exercise, this is a metric. You can sort of check all the properties also, but I could have written this as f minus g in absolute value in norm in C0. Okay, that's a metric. I can say something like this. A sequence, let's say f1, f2, f3, dot, dot, dot. All of these, I want to be index x. And let's say that I have f infinity converges uniformly to f infinity if, well, the d of f sub n and f sub infinity goes to 0 as infinity goes as n goes to infinity. This is actually the definition of uniform convergence. As you see, so much nicer in a sense compared to pointwise convergence, because it turns out that stating what it means for a sequence of functions to converge pointwise in terms of metrics is a lot more complicated. In fact, it is impossible, but never mind. And so somehow, because of properties like this, it turns out that these sort of strong notions of convergence often can be captured by an appropriate metric, let's say. And if we have something like this, of course, you also know from 3210 that the integral of this converges to the integral of this. Also, this, again, as n goes to infinity, converges to this guy. Now, we had talked about how integration is a linear transformation. And so, in a sense, this tells you something about the continuity of the operation that takes a function and gives back its integral. Okay? And so, first 2 weeks we were talking about vector spaces, norms, all that stuff. And now we're talking about metrics. Ultimately, all of these are so that we can compress a lot of the structures that you started working with in 3210 and previous classes probably, and sort of use them in a more efficient manner. i.e. integration linear transformation, maybe I should say the linear transformation that is integration is continuous. Right, so I have, I say this is my integration. I takes f, or f sub n, to this number. So it goes from x to the reals. I have a sequence of points, f sub n, that converges to something. And I'm saying that the outputs too converge to the corresponding output. Okay. This is just the reason why this is an exercise is for you to sort of think about this, remember that these are indeed the case from 30 to 10 and so on. So what we're going to do this week and next week is to clarify things like this continuity and stuff like that. Basically, we're going to upgrade all of these notions that you learn in 30 to 10 and basically wrap them in the context of metric spaces. Questions? Okay. So now let me introduce sequences and subsequences. That's how we started. That's one way to start, talking about continuity, at least in the context of metric spaces. But of course, I can always take a sequence in any set whatsoever. I cannot quite talk about the convergence of something without having something like a metric. So let x be a set, a function from, let's say, non-negative integers to x itself is a sequence. So in a sense, there is no fundamental distinction between a sequence and a function. It's just that when you say a sequence, at least in math, you're alluding to the sort of implicit assumption that your input space, your independent variables, is infinitely many integers that go to infinity, at least in one direction. There are other contexts where you also allow for negative time, but for our purposes, mostly this turns out to be sufficient. Typically, I'm going to denote this by x bullet, okay? Denoted by okay, so I'm going to write it like this. So bullet is where the time goes for me. Okay, so this is the placeholder where you plug in whatever time you have. Of course, other notations for these are things like this. X sub n, like so, or x sub n, or x bracket n. Depending on the field that you're looking into, the notation changes. Okay. If D is a metric on X, and let's say X infinity is a point in X, I'm going to say that the sequence x bullet converges to x infinity if the distance between them, that is to say, the distance between the nth element in my sequence and the target point converges to 0. X bullet converges to x infinity if, well, I'm going to look at the distance between x sub n and x sub infinity for any fixed n. This is now a number. It's a sequence of numbers. I know what it means for a sequence of numbers to converge to 0. So I'm going to use that. Okay. And so, in short, I can write things like this as well. Questions? Okay. Now we said in the first week and second week, oh, well, whenever you define a structure, you immediately want to talk about or think about or define what it means for a function to preserve that structure. When it comes to metrics, there are a couple different ways of defining what it means to preserve that structure. It turns out for the purpose of calculus, you don't want to just say it preserves the metric, even though that is an important concept, which leads to this notion of an isometry. In general, you want to, the structure that you want to preserve is convergent sequences. And I'm going to say a function between two metric spaces is continuous if it preserves convergent sequences. Metric spaces. F be a function from x to y. I'm going to say that f is, let's say, continuous at some point. Let's say x, let's say x infinity be a point in x. Then f is continuous at x infinity if for any sequence converging to x infinity, f of that sequence converges to f of x infinity. Okay. So one way to think about sequences like this is I have some space x, some set. These are the sort of values that I'm interested in. And a sequence in that set is a signal. Okay, I'm just recording certain positions, perhaps, whatever. And so here's the heuristic. Here's my x. Here's my y, and f goes from here to there. I have some target here, which is x infinity. And under f, it goes to something, f of x infinity. Continuity means continuity at x infinity. No matter how I take my signal that ultimately stabilizes at x infinity, if I were to look at the images of all of these data points under my f, the outputs converge also. Okay? So writing this out more explicitly, if these are all points in X such that limit as n goes to infinity of the, so the metric in the input space between x sub n and the target x sub infinity goes to 0, then now I'm going to apply f to this. So I have f of x1, f of x2, f of x3, and so on, which gives me a signal in the output space. Okay. I want that output signal to converge to the corresponding output. Okay. Questions? Did you all sign this? Yes. Oh, go ahead. Yes.
So make sure the dx and dy are just metrics. With
Yeah, so dx is the metric on x, dy is the metric on y.
Okay.
Yeah. And of course, I'm going to call a function continuous if it is continuous at any point, just as in 3210. This was some heuristic. Definition continued. Continuous at x infinity for any x infinity. The set of all continuous functions from x to y is going to be denoted by C0, so that's continuity always, x semicolon y. This is already toward calculus. At this generality, we can't quite talk about differentiability, it turns out. I mean, we can, but we're not gonna. So I'm already sort of incorporating this idea of, well, this is the 0 times continuously differentiable functions. Okay, I don't get to differentiate, but at the very least, the 0th derivative, so to speak, is continuous. And then one more definition. A homeomorphism is going to be, well, basically like a linear isomorphism. So you get to invert, but not in the context of linearity, but in the context of continuity. Homeomorphism. Okay. Let's write it smaller. Is a continuous f from x to y that has a functional inverse, so f inverse exists from y to x, and that too is continuous. That has a continuous functional inverse. And I'm going to denote by homeo x semicolon y the collection of all homeomorphisms from x to y. I had defined all of these in 3210, but probably many of you who haven't taken 3210 from me, so this is the first time you're seeing these ideas. I thought it would be good to sort of go through all of these things. My suggestion is that when you're trying to understand these concepts in, when you're trying to understand these abstract concepts, just focus on the most simple situation. For instance, take x and y both to be the unit interval, 0, 1, and try to see what is a continuous function, what is a non-continuous function, what is a homeomorphism and stuff like that. So for instance, example, let's say both of these are 0, 1 with the subspace metric, with the induced metric. I'm not sort of using a bizarre distance. These are supposed to be numbers within the real line. So I'm using that standard metric, okay? And so any function then from x to y I can think of as basically a shape in this square. Okay, that's a function. This is y equals x. F of x equals x if you want. Certainly, this has to be continuous because it is linear, but we'll see that later perhaps. But I hope you learned in 3210 how to think about continuity in terms of sequences. Okay, so if I were to take any point here, x infinity, its output is this height, and then if I were to take any sequence, it doesn't matter. It can go this way, maybe it goes this way, whatever. But of course, in the y-axis, you're just going to duplicate everything, right? So this function is continuous at every point. What is its inverse? To come up with the inverse, you need to flip this picture. The inverse is itself. So this is a homeomorphism. Here's another example, maybe like this. This too is a homeomorphism, for instance. F inverse, geometrically, just means flipping the graph along the main diagonal. So that's F inverse. Both of these are continuous functions, of course. Homeo. Here's the final example for today. Let's say here's a flat piece. It goes up. This is not a homeomorphism, you see. So this part is supposed to be flat. When you flip this, you can flip it geometrically, but this function fails this so-called vertical line test. Right? It doesn't even have an inverse, but it is continuous. The point of all this formalism is that it's robust in that instead of looking at single variable functions that are nice that you can draw, the same formalism applies to more complicated, maybe infinite dimensional spaces also. Okay? Okay, I think that's a good place to stop. Thank you. I'll see you tomorrow. Okay, let's start. Good morning. So a couple of things. We have, according to the schedule, 4 more classes on metric spaces. Probably, I'm estimating it's not going to be enough. So probably what's going to happen is after the first midterm, which is next Friday, not this Friday, but next Friday, we were supposed to start differential calculus, but maybe we're going to take a couple of classes from week 5 and discuss more sort of properties or theorems around continuity, things like this. If anything, if needed, probably we're going to get rid of some of the topics that I had scheduled for week 8. And these are sort of topics that revolve around optimization, first derivative test, second derivative test, Lagrange multipliers, Hessians, all that stuff. So if anything, maybe we'll sort of cut that short a little bit. So we have a bunch of things to cover. And I'm going to introduce more and more terminology. So I thought it would be a good idea to take a second, have a look at all the structures that we have defined so far, remember some of these concepts, and then I'll sort of start mentioning some of the topics that we might end up needing to discuss eventually as well, depending on these different contexts. Okay? So essentially, we have 2 different categories. These are related, of course, but one category is when the underlying space is a vector space. That is to say, you have a set with addition and scalar multiplication that works. So these operations work the way you expect them to. And then on this, we defined 3 different things: inner products, norms, metrics. And yesterday we said, okay, let's put that aside. Let's consider an abstract set X, and we're going to define a metric D on it. And then we started talking about some of these things. So let's try to talk about some of the concepts that we mentioned. For instance, if X is a set, of course, the notion of a function requires only sets, right? You don't need anything more. Functional inverses, right? X goes to y, y goes to x. So F inverse, number of elements, it turns out to be the thing that is very important, at least in the context of amorphous sets. So this is formally called cardinality. Different sorts of infinities and stuff like that, which we're not interested in, at least in this class. But if you end up taking a class in what is called set theory, cardinality ends up becoming very important there, different infinities. If you have vector spaces, of course, we have the notion of linearity. Linear transformations, linear isomorphisms. Dimension, basis, linear combination, span, blah, 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 all of these things, right? These notions don't require anything except addition and scalar multiplication. So now I want to ask you, if I have an inner product, what sort of things do I have access to now? Maybe these are concepts, or maybe important sort of inequalities, statements, things like this. Orthogonality, yeah. So you need an inner product to talk about what it means for 2 vectors to be orthogonal, which means, for instance, if you want to think about orthonormal bases, you need an inner product, O and B. What else? Of course, more general than orthogonality, angles. Orthogonal projections is one thing, right? Another notion that you're going to see in the second problem set is the notion of an adjoint. So if you have a linear transformation L, there's this adjoint, which is L star. So in physics and other areas, people talk about self-adjoint operators. This is basically the same thing in the language of 2270, symmetric matrix. Okay, this is a very important notion. Adjoint operator. There is one more thing that is very important that becomes available once I have an inner product, and that's an inequality. What was that inequality that was very important? Yeah, CBS. By the way, I said that Bunyakovsky was a Soviet mathematician. Technically, he wasn't. He was so before the Soviet Russia, there was the Russian Empire. So he lived around that time. And even then, he was born and lived in what I think now would be classified as Ukraine. So that was like a historical or biographical mistake on my part. There's like street names and stuff, streets names after Bunyakovsky apparently in Ukraine. You can read all about his achievements and stuff like that on Wikipedia. So we have these. Once we have a norm, what type of things do I now have available to me? What type of notions?
I mean, like distance from the origin.
Yes, but it is a different part. So maybe it's kind of hard to say, but maybe one can say triangular inequality. Of course, this is one of the axioms of a norm, but kind of works backwards too, I would say. So you're sort of like, the reason why this notion is defined using a bunch of axioms, one of which is the triangular inequality, is that people realize that sort of packaging this structure becomes very useful, right? So you sort of like abstract it out in a sense. That's actually all I could think of. When it comes to a metric, and so we said that from a norm, you can define a metric. And so now I'm going to keep continuing from here. And so when you have a metric, of course, again, you have the triangular inequality. And then what else did we define? We defined convergence, and convergence of sequences and continuity. And here are different structures that I added. We have the metric structure. This is a new word, at least for some of you. Uniformity. Then you have another structure, topology, and pretty much the final sort of level, which is measurability. It turns out that convergent sequences are really in this context of topology. So and so is continuity. Homeomorphism, right? Okay, so now let me add a couple more words. And these are, now I'm going to write in red, these are going to be phrases that we're probably going to see at some point. If I just stick to this structure of the metric, Lipschitz or Hölder functions, or more generally, there is something called the modulus of continuity of a function. So you know continuity involves, there is a characterization of continuity for functions that involves epsilons and deltas. But typically you say for any epsilon there is a delta such that something happens. But often it is not clear what is the dependency of delta on epsilon. And so this modulus of continuity is a quantitative way of describing which delta you should choose to get whatever epsilon you need. So we might be able to talk about it eventually, or maybe you'll see it in the problem sets. So modulus of continuity. From an abstract point of view, of course, you say, OK, this function is continuous, whatever. But if you're doing things that are more toward application, that is often not enough. You also want to quantify how continuous a function is. This is also not the only way, but they're one of the main ways, let's say. Now, here's the next structure. This arrow is supposed to indicate that whenever you have a metric on a set, you also define a uniformity. And then whenever you have a uniformity structure, you have a topology structure as well. And any topology structure implies or induces a measurability structure, just like the inductions here. The difference here is that these three structures are somewhat more abstract to describe. So as opposed to saying, oh, I have this function that satisfies these axioms, right? So we defined all three of these like that. We said, oh, I want a function that takes this and that, turns these things into numbers, whatever, satisfying 4 or 5 axioms. These structures, on the other hand, are defined by singling out certain collections of subsets as special. Okay? So it's a different way of defining a structure. I'm not going to define these things formally, but at the very least, I wanted to describe some of the notions that we're going to be describing, that we're going to be using. So for instance, while continuity is really associated to the topological structure, uniform continuity is associated to the uniformity structure, surprisingly. And for instance, while convergent sequences or divergent sequences, that's about topology, Cauchy sequences, which I hope you remember a little bit from 30 to 10, really is about this uniformity structure. So uniform continuity. Another word that I hope you remember from 30 to 10 is the notion of completeness. That too is about uniformity. Completeness. There are many notions of completeness, of course. And in fact, even in 30 to 10, you see two different at least kinds of completeness, but never mind. So this, we're going to define what this means. And so this measurability is pretty much the last stop when it comes to different types of structures. It's the weakest kind of structure, at least at face, like if you take it at face value. And if you don't have measurability, you don't have pretty much anything. And I'm just going to say here that this really is something that you study in an advanced analysis class, where the main focus is what is called measure theory. So this is an advanced thing. It's not very complicated, but it takes time, and partially because measurability is defined in terms of collections of subsets, it's somewhat abstract and sort of hard to get accustomed to. The style kind of changes. That's why this is more advanced, and we're not going to do it. But later on, when we start talking about Riemann integrability, we're going to start talking about something called Jordan content or Jordan measurability. So these notions are really sort of a proto-version of measure theory somehow. And that's why I'm thinking of de-emphasizing it, these Jordan stuff. Jordan content. Jordan measurability. Maybe I should add a couple more words. In the context of topology, we're going to have also words like open, closed, closure, interior, boundary, compact, these types of things. Closed, compact, connected, path connected, closure, interior, boundary, bunch of different things. There are many sort of words in this context, but we'll get there. We'll start talking about them when we get there. Okay. So I just wanted to mention all of these. So these notions, for instance, are really about uniformity, and these notions are really about topology and stuff like that. But I'm not going to define topology and uniformity, and really I'm just going to consider all of this as like one blob, pretty much. Okay? But on the other hand, just so that you know, each of these structures are different structures, and mathematicians study them separately. Okay? And so you see, when you take 2270 or the standard calculus series, this is your space, and you have the dot product, and of course you have addition and scalar multiplication, and then you have the dot product. And you don't really distinguish which structures come from where, ultimately, and which notions come from where. Part of the consequence of that is that I think it becomes more confusing. But at the same time, there's less terminology in a sense. And so when you, as you're upgrading your notion, your understanding of mathematics, you start separating your structures, okay? These are now different structures that we're sort of taking one by one, in a sense. Let me see if I missed anything that is important. I think not. Any questions about these? This was like a short summary and what is to come in terms of new concepts. And so whenever you're getting confused about things, it might be a good idea to look back at this sort of flow chart in a sense. So for instance, you might see phrases like completeness is not a topological notion. This is really what they mean. So you might have two metric spaces that are homeomorphic to each other, that are equivalent to each other in the sense of topology, but their uniform structure are different, for instance. A bunch of things. Another thing you might ask is, well, can I reverse any one of these arrows? So for instance, if I have a vector space, I know that any norm defines a metric. How about vice versa? If I have a metric that is reasonable, let's say, can I reconstruct, can I figure out the norm it comes from? Sometimes you can. It turns out that this is not that hard, actually. And that's going to be an exercise. Not that hard relative to the next exercise I'm going to mention. If B be a vector space, D a metric on V, then there is a norm that induces D. So you get to rewind this arrow if and only if D satisfies certain properties. by a norm if and only if, well, you look at the properties of a metric induced by a norm, and you just like assume those properties. The Cx Cy equals C in absolute value dxy for any constant c, for any scalar c, and for any two vectors x and y. And so this is the homogeneity property if you want. And translation invariance. The distance between x plus c and y plus c should be the same as distance between x and y. In this case, it turns out that you can just define the norm of x to be the distance of x to the 0 vector, and this turns out to satisfy the axioms of a norm, for instance. So this is how this is like the complete solution for whether or not you can rewind this arrow from here to there. There's a similar statement that reverses this arrow. Its statement is not that hard, but its proof is somewhat involved. So I'm just going to state it, but this is a hard exercise. And in fact, let's give a name for it. This is the Jordan von Neumann theorem, not the same Jordan. Different Jordan. And this von Neumann is the von Neumann you know, if you know of von Neumann. There's only one von Neumann that is known by a lot of people. So computers, whatever, quantum mechanics. So let E be a vector space, then let's say a norm on B is induced by an inner product if and only if the so-called parallelogram identity is satisfied, or the Apollonius identity is satisfied. Which says that for any two vectors, what does it say? Norm of x plus y plus norm of x minus y is twice norm of x plus norm of y. So one direction is not that hard. If you know that a norm is induced by an inner product, you can just open these up. I think there are squares here. OK, everything's squared. If you know that the norm is induced by an inner product, you can just open everything up, write everything in terms of the inner product, and then use the bilinearity property to sort of see what cancels out, and this shows up. Now the reverse procedure, where you have a norm that satisfies this property, can be sort of reverse engineered to come up with an inner product. That is a harder part. Okay, so this is a hard exercise. I was thinking of doing it, but I decided it's not really fundamental. But probably if you take a class that focuses on vector spaces, you would encounter this exercise. Questions? Similarly, people are interested in reverse engineering these. So people would ask, oh, I have some topology on a set, so I have a topological space. Is it they would ask metrizable. That is to say, is the topology I'm looking at, is the notion of convergence I'm looking at, really induced by a metric? For instance, yesterday I said pointwise convergence of functions actually does not come from any metric whatsoever. I just said that as sort of like a factoid. It's really not our sort of concern in this class. But people are interested in this, or they're interested in whether or not a certain topology is uniformizable, for instance. Bunch of different things. Especially in the beginning of the 20th century, people were really interested in these types of questions. Nowadays, these types of questions are pretty much all answered, and it's sort of not that trendy anymore, even though some people probably are still sort of looking into these things. So reverse engineering, these arrows are pretty much all sort of complete at this point. And frankly, somewhat tangential to a regular mathematician. Okay. Now that we did this, okay. Any questions about any of this? Let's go back to convergence and stuff. So, like I said, I'm just considering all of these as just one blob of metric structures, basically. Yesterday, we defined what it means for a sequence in a metric space to be convergent. I hope at this point, if I were to tell you that if a sequence converges, that limit has to be unique, you won't be surprised. Probably you prove this in 30-10 for reals, but it is true for any metric space whatsoever. So I'm going to leave it to you as an exercise. And in fact, it is proved using the exact same proof. If a sequence in a metric space converges, the limit is unique. Okay. In terms of applications, perhaps one of the best applications of this is this, right? So you have, let's say, a sequence of functions, and you're asking, does this sequence have a uniform limit? So does the sequence converge uniformly to some function? And if possible, you would want to compute that limiting function as well, right? And one method is that you know that uniform convergence implies pointwise convergence. And because limits are supposed to be unique, what you can do is you can first look at the pointwise limit. That would give you a function. That would be your candidate uniform limit. And then see whether or not the limiting procedure that you're looking at is actually uniform instead of pointwise. Okay, so that's sort of one application of this idea. That's that. Okay. So here's a nice, not very complicated, but very useful statement. Reverse triangular inequality. Right, so if I have a metric space X, we mentioned how if I were to take any 3 points, the distance between these 2 points plus the distance between these 2 points should dominate the distance between these 2 points. That is a triangular inequality, and that's an axiom. Okay. Reverse triangular inequality is pretty much the same thing, except that you somewhat write the distances in the backward direction. And instead of having a plus on the right-hand side, you want to have a minus on the left-hand side. Let X be a metric space, then for any x, y, z, I have this. Oop. That's a statement. Okay. This is surprisingly very useful. Okay. So let's try to prove this. And you see how, even from a pedagogical point of view, it is perhaps useful to separate the structures. Because now that you know a metric space is just a set with a metric on it, and if I'm stating this as a statement to prove, the only thing you can use are the axioms of a metric. Right? So you're going to have to use exactly 3 things, or at most 3 things. Of course, ultimately, this is also true in an inner product space, but I'm not going to use anything about angles, for instance. So how can we prove this? Any ideas?
I mean, we could just rearrange it until it looks like the triangular inequality.
Essentially, right? Yeah. And so the way I thought of doing it is like this. And I'm going to use this very simple idea. On the left, I have an absolute value. And so really the form of this inequality that I'm trying to verify is like so. I have one quantity, A, that could be negative, right? So if I didn't have the absolute values, maybe this is a negative number. So I'm trying to show this. Okay? This is equivalent to saying that both A, and I know that the right-hand side is non-negative because metrics, so distances, are non-negative numbers. It is equivalent to show this. So this is equivalent to showing that both A is dominated by B and minus A is dominated by B. It's very simple, but it's very useful. Okay? Minus A. Of course, either A is equal to the absolute value or minus A is equal to the absolute value of A, right? If I have a number. Okay, so I'm going to use that. So for instance, what I can do is this. I can look at d of x comma y, distance from x to y. By the triangular inequality, I know that this is dominated by d of x comma z plus d of z comma y. Okay? This is the triangular inequality. Now, if I were to take this to the other side, I almost have that, except that I don't have the absolute values, right? Okay, so the orders here are different, but one of the axioms of a metric is that the order in which I plug in the points doesn't matter. So I have this part. So I have this. So this is this part, okay? This I proved. Now I need to show that this distance minus this distance too is bounded by this distance. And so instead of starting with this guy, I might as well just start with this guy and pretty much apply the same idea. Again, by the triangular inequality, if I inject a y in here, this is going to increase like so. Then taking this to the other side, let me write it like this. This is minus dxy minus dxz in parentheses is bounded from above by d of yz. Okay, so this is my A in that form. This is my B. Here is minus A. And again, this is B. I showed that A, both A and minus A are bounded by B. Which means that this has to be the case. So that's the end of the proof. Very simple. I'm just reordering things, basically. Just using the definition. But you're going to see throughout this class, this is a very useful inequality. Any comments or questions? Should I repeat the argument? Yes? No? Yes? You might as well. OK. So it's all a matter of choosing the right points, basically. I have 3 points, ultimately, x, y, and z. And I can just plug in 2 inputs, right? And so the only thing I can leverage at this point is I'm going to fix 2 points, and I'm going to inject the 3rd point that I didn't use into the inequality to get this bound. And so all I'm doing is I look at what I'm trying to prove. Okay, I have here on the left-hand side. And I say, for instance, well, if I didn't have the absolute values, this would be pretty much the triangular inequality, right? So, because if I didn't have the absolute value, I could just take this to the other side, and that would be the same thing as a triangular inequality. So that's the starting point. And then I say, oh, once I have that, how can I handle this absolute value? Then I say to myself, oh, to handle the absolute value, all I need to do is to make sure that this quantity here is non-negative, right? That's what the absolute value does. And so either this is non-negative without absolute value, or the order is flipped. And that's how I thought, oh, maybe I just change the orders in which I apply the triangular inequality to get the other thing. And indeed, based on this observation, that ends up being sufficient. Does this kind of make sense? Okay. I am 90% sure that if you were to look at the part of the textbook that you studied for 3210, you're going to see this expression. Maybe different letters. But you're going to see this expression. This is just saying, this is just triangular or reverse triangular inequality for the specific metric that is the difference, rather, that is the absolute value of difference of 2 numbers. Okay. The point is that you don't need, really, for the statement that this is the specific absolute value function. Any metric that, any function that satisfies the properties of a metric has the same property. And again, let's observe that these bars are actual absolute values, right? Because this is a number, this is a number. I'm taking the difference of 2 numbers. When I put bars, that's the absolute value. OK. Now, product metric spaces. So if I have, well, we talked about metric subspaces. And remember, in the context of linear spaces too, we talked about linear subspaces. In this other structure, this structure of the metric, we had metric subspaces. And just like I can look at the product of two vector spaces, and that too is a vector space, you just add entry-wise. You use that in the first problem set when you were talking about the graph of a function, for instance. Well, I can try doing a similar thing in the context of metric spaces. I would like to think of the product of two metric spaces as a metric space in and of itself. There are a couple different ways of doing this. Let's write it like this. X dx and y dy, the metric spaces and let me take a p-value. I know we didn't show that LP norms are norms, but we can just assume this. Then the LP metric, LP product metric, let me say, metric on x times y. This is a set of all those pairs, x comma y, where x comes from capital X, lower y comes from capital Y, is the following. x1, y1 is one point in this product space, product set. And so I want to define the distance of x1, y1 to the point x2, y2. And of course, I want to define it in such a way that somehow this distance is related to these two distances. Well, what you can do is you can just look at the first components and measure their distances using this metric, and then look at the second components, measure their distance using this metric. And then you can look at the, for instance, LP norm of this vector, so to speak. Here's what I mean. Take the first entries, look at the distance between them. That's a number now. Then look at the distance between the second entries. That's again a number. So this is a pair of numbers. That's a vector in the plane, which means that I can look at its LP norm. Which means that this is dx x1 x2 to the power p plus dy y1 y2 to the power p, all raised to the power 1 over p, if p is less than infinity and the max of these two distances otherwise. So max I'm not going to verify that this is a metric. I can just take it as a fact. One thing I'm going to leave to you is this. So any one of these is a metric on x times y, so that the product of two metric spaces, again, is a metric space. It's the product metric space. And so I want to think about what it means for a sequence in that product to converge. Okay. Exercise. X bullet, Y bullet. That's a sequence. I'm even abbreviating the notion of a sequence. Whenever I have a bullet, that's a sequence of numbers or values. Converges to x infinity, y infinity, and x times y relative to any one of these metrics, in fact. For some or any P, if and only if yeah, let's write it like this. Oh, x bullet converges to x infinity in x, and y bullet converges to y infinity in y. That is to say, whenever you have a product metric space, and when you're looking at convergence in that product metric space, all you need to do is look at the convergence of components. As a special case of this, of course, convergence of vectors in Rn. So let's write it like this. Let's say this is first component, second component, and so on. That's a sequence of vectors in Rn, or maybe we should use a different letter. D converges to x infinity, which is again the vector with components x1 infinity, x2 infinity, dot, 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 x d infinity. If and only if xi bullet converges to xi infinity. So in a sense, continuity is sort of continuity of a bunch of sequences. Continuity of vectors is continuity of its components. Nothing very complicated happening in the sense of continuity. And so given this, I'm going to give one more exercise, and maybe we can discuss how to do this, at least one part. I'm going to connect inner products and norms and stuff to continuity now. Any inner product turns out to be continuous. Any norm turns out to be continuous. And any distance function itself turns out to be continuous. If this is an inner product space, then this inner product considered as a function like this is continuous relative to the distance it defines. B is a norm space the norm itself is continuous. I'm running out of time, so I'm not going to finish this. But likewise, distances, and in fact, vector addition and scalar multiplication too, turn out to be continuous whenever you have these things. It's hard to even make sense of what this means, in a sense. We'll talk about this on Friday. OK, thank you. OK, let's start. Good morning. Today we're going to keep working on metric spaces. So our first midterm is due next. It's going to be next Friday. So we're going to have class next Monday and Tuesday. We're going to review on Wednesday, and Friday it's going to be the exam. By the end of today, you're going to receive an email from me describing what are the topics, how you should prepare, things like this. General information about the exam. Are there any questions?
Will problem set 2 be graded by the exam?
Hopefully, yes. Same question, yeah. 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 Yeah, for instance, for problem set 1, I graded my part, but I'm waiting for our grader to finish their part. So.
Would you be able to release that for us to study? Or?
Yeah, I mean, hopefully it's going to be released today for problem set 1, yeah. I'm hoping that I'm going to be able to return the grades within a week, which is sort of the standard timeline. Last semester, I worked with the same grader, and we were able to sort of grade things, problem sets before the midterms. So for instance, if we end up being able to, adhere to the same schedule, hopefully by Wednesday evening, you're going to receive your grades and the solutions for problem set 2 too. But, the complexity of the problems in 3220 is a lot more. It's much larger, much higher than 3210. So we'll see. Anyway, any other questions? Okay. I should also mention, in any event, you can always send an email and say, oh, can you have a look at my work, and if anything sort of pops out, can you tell me perhaps things I should be worried about a little bit, or things I could write better or describe better, things like this. Okay. So I mentioned on Wednesday how basically one problem from each problem set is going to be graded for accuracy. So if you want to understand more and if you want more feedback, you're going to have to reach out to me yourself and maybe set up an appointment or ask over email and stuff like this. Okay. Any other questions? Okay, so I thought of this exercise, basically rewriting history. I want you to go back to your textbook or your notes from 3210 and sort of reinterpret every single statement, or the statements that you feel are relevant to what we're doing now, and sort of try to generalize them. So for instance, whenever you see an absolute value there, think, can I actually interpret this as a norm or of some space? Or if you have an expression like this, can I think of this as a metric on an arbitrary metric space? Okay, you're going to realize often you are able to do this. And part of why I was using this notation for a norm is so that it's easier to sort of transition from single variable to multivariable. Because in my head, even though obviously there are things that are different, in my head, absolute values and norms are pretty much the same thing, right? So part of it is because I know the material by now. But it's also, knowing something is somewhat about having shortcuts, mental shortcuts as to how you think about these kind of things. Right? So when you think about chess, for instance, like a grandmaster doesn't look at every single thing and tries to compute everything, right? So looks at the board and already has an idea what should be done or what shouldn't be done, something like that. Because a grandmaster in chess, for instance, develops all of these mental shortcuts. A similar thing happens in math. Okay. So to recap, we had this metric space, so a set together with a special function called a metric or a distance function. And so D was a function that takes 2 points in my set X and gives me back some non-negative number that is supposed to mean the distance between these 2 points that I chose. So this should be D of X comma Y should be distance between X and Y. Okay. So we have this new world of metric spaces. And I had this notation x bullet, and I said, when I say x bullet element x, that's a special notation for saying this is a sequence in x. I'm just abbreviating a bunch of things. And then I have x infinity. It's 1 point now. Okay, so this is a sequence of points in x. This is 1 point. So this bullet notation is a specific, it's like it's a different data type if you want. One specific point. And this was the shorthand notation for the statement that x bullet, the sequence converges to x infinity. And how did we define this? We said that x bullet converges to x infinity if, well, the sequence, that is the distance between x sub n, a typical element in my sequence, or typical term, and x infinity converges to 0. So you see, this is a function of n, and it takes non-negative real values. And so I can ask that this converges to 0. Okay? And so then, of course, what you can do is you can ask, what does that mean? From 30 to 10, of course, this is a specific thing. It has a formal definition. Maybe I should ask you, how can I sort of expand this? What is the formal definition of the limit of this sequence of numbers converging to 0? Just to reiterate. That's a real number. What is this underneath when you open it up?
It's like a couple of supremums and infimums.
You can define it that way, but what is the
Like,
most vanilla way of defining this?
isn't it like when lim sum equals lim in?
I want it even simpler.
Uh,
For any,
oh yeah, it's this again. For any epsilon, like there exists an n such that this is less than the epsilon.
Yeah. Yeah, your colleague knows this because in 30 to 10 I wrote this statement a billion times like a madman. And so for any epsilon, for any error margin, right, there is some time capital N, say like this, such that any term after this capital N is going to be within an epsilon of the target. You guys remember this statement? Maybe they didn't sort of describe this using logical symbols, but I am a big fan of logical symbols like this because it allows you to just write everything down with complete accuracy. And you end up not needing to think about how to write things down. So for instance, in the textbook, they don't use the logical symbols. They say it's like this, and then for any epsilon, there's an n such that blah, blah, blah. And then here they write for any n after capital N. The point is that from a logical perspective, it turns out that you can write pretty much any mathematical statement in this form. A bunch of logical quantifiers and then the statement. And so just get accustomed to writing it like this. You don't have to, of course, but I would highly recommend it. And then once you get comfortable with these ideas, you can just sort of become more sloppy about the logic underneath. And what does this mean? Let's draw the situation again, because hopefully today we're going to start talking about Cauchy sequences as well. Convergence of a sequence of real numbers or any sequence of a sequence in any metric space whatsoever always is based on the following idea. You have a bunch of points. Let's in fact draw it like this. This is my time. It's the independent variable. The vertical, even though I drew it as a line, think of it as a sort of caricature of some abstract space. Goes on like this. In a second, I'm going to draw a more geometric picture as well. So I'm sort of drawing the so-called space-time diagram, if you want. This is the space. Sorry, this is the time. This is the space. If you're doing physics, you do it the other way around. Time goes upwards somehow in physics, but in math, typically this is what we do. And my x bullet is a signal taking values in this capital space X. It could be real numbers. It could be some function space, whatever. Maybe it's like this. Okay. And in a sense, the point of a limit, this x infinity there, is something like a summary of this whole sequence. You collected a bunch of data. You want to summarize this complicated object using one thing. If your signal if it's taking values in the reals, then your summary, your limit, should be a real number. If your signal is taking values in a more complicated space, probably your summary is going to be complicated in a similar fashion. Okay? And so now let me try to draw a more visual picture. So for instance, this would be x0 and then x1, x2, the heights I mean. And then x3, x4, and so on. In the geometric setting, what happens is this. Somehow you figure out that there is some sort of candidate for a summary of your signal. And your signal now is taking values here. Now, what is the difference between this diagram and this diagram? This is a space-time diagram. Here, I'm not going to show the time part. I'm only going to show the space. Okay? Because this x is sort of like a blob. I don't know how it looks, really. And so maybe this is what is happening. Okay, so it's going like this, etc. Things happen. I get to say that this x infinity that I somehow came up with is the best summary in a specific sense, in the sense of limits, insofar as the following happens. If I were to take a small, what we're going to call ball of radius epsilon, okay, so now this is my ball in x, centered at x infinity, of radius epsilon. So the way I think about this is that this is sort of like a fuzzy summary, okay? It's not an exact point, but it's approximate. It's like a cloud. And so if I were to take, for instance, epsilon equals, let's say, 1, that's a 1 cloud. So cloud of size 1, if you want. In order for x infinity to be an appropriate summary for my signal, what needs to happen is that if I wait finite time, so I'm saying this is time 0, time 1, time 2, and so on, I wait finite time, this capital N, and after that, I am guaranteed that my signal is taking values in this epsilon equals 1 cloud. But not only for epsilon equals 1 cloud do I want this. I want to be able to shrink epsilon as much as I want. Okay? So you say, OK, so if I wait time until time n, let's say, or n sub 1, I am guaranteed that my signal is going to take values within this epsilon equals 1 ball. But you want to say, what if I were to try to decrease the error margin? OK, so let me redraw this again. I'm going to get rid of this part. So now I'm zooming on to this part, OK? I'm going to draw it again. Here's my epsilon equals 1 ball. And then let's say here is epsilon equals 1/2 ball. It's a smaller ball. Epsilon for me is the error margin, right? And what we said so far is that my sequence, my signal had started somewhere, and then I waited until time, let's say, n sub 1, capital N sub 1, and then I know, let's say, that after this n sub 1, so this is, for instance, n sub 1 plus 1, the next time, next iterate if you want, and it goes somewhere else here, and it goes somewhere else here. Maybe it gets even closer, or maybe it jumps out. Okay? All I know is that my signal does not escape this epsilon equals 1 ball after time capital N sub 1. Then I shrink my epsilon to, let's say, 1/2. I still want the same thing. So for instance, in this picture, what we saw is that initially my sequence was taking values within an epsilon equals 1 of the target. And then it get closer, and then it escaped again. For convergence to happen, what needs to happen is that there should be, again, sometime, let's say, n sub 2. Quite possibly n sub 2 is going to be greater than n sub 1. It's going to be a later time, such that after this, again, I am guaranteed that my signal stays now within this smaller ball. And then I want to keep going. Okay, I want to have the same statement for, let's say, epsilon equals 1/4, 1/8, and so on. Insofar as I can do this, I get to say that x will converges to x infinity. The point is that this abstract definition of a metric does not require that your balls look like this. In the plane, within the Euclidean metric, they do look like this. But in general, for an abstract metric space, the same mentality holds from a formal perspective. Okay? So again, there's a trade-off. When something works for many situations, it's harder to visualize them. And so it becomes harder to think about a sequence of functions converging to a sort of target limit using the supremum metric or C0 metric. But somehow, you can still think about that in these sort of geometric terms. And this class is going to be all about sort of leveraging both of these ideas, abstraction on the one side and intuition on the other side. Any questions about this? OK, so I had mentioned as an exercise, as a general exercise, go back to your 3210 notes or textbook, whatever, and think about how you can sort of generalize the statements, especially when you see an absolute value or the absolute value of the difference of two things. or maybe the product of two things, two numbers, for instance. And so let's think about this. So when it comes to sequences, for instance, there's a theorem whose proof I think is not written in the textbook. It was given as an exercise, which then I put in one of the problem sets when I was teaching. Limit theorems for sequences of real numbers. So this is 3210 material. What do we remember about these limit theorems for sequences? Any ideas? Is this too easy? Is that why you're not saying anything? Because otherwise you're going to have a hard time in this class.
There's like, this one.
You good? Yeah.
If it's bounded by above and it's a non-decreasing sequence, there's a
Sure, but that is more complicated than what I'm asking. That's the monotone convergence theorem. That is one thing that we're not going to have here, actually. Because if you have like a higher dimensional space, how are you going to say this vector is larger than that other vector? We have magnitudes, but vectors could be in different directions. So that's going to be one thing that we don't have, actually. But what are some simpler statements? If I have two sequences, what can I do with those two sequences? Let's say I know that they converge.
Then the limit, say they're like called x and y, then the limit of x plus y is equal to the limit of x plus the limit of y.
Right? Insofar as these two things converge, and that's a requirement, right? Otherwise this doesn't work. Do we remember something like this? What else? What other limit theorems do we have for sequences of numbers? Yeah.
If we have a limit multiplied by a scalar, we can move the scalar outside.
And in fact, I can even generalize that, and I can say the product of, I can take the product of two sequences. And I can divide and stuff like that too. Oh, maybe I should write it like this. And then, for instance, one thing you can say is that if a sequence converges to something, certainly the absolute values converge as well. Because absolute value is a continuous function, you could say. There are many more, of course, but these are the fundamental ones. So for instance, a version of this product rule says that if you have the ratio of two sequences, insofar as the denominator doesn't converge to 0, the limit of the product, or the limit of the ratio is the ratio of the limits, and stuff like that. We have a bunch of things. Now let's try to think of these in higher dimension. So first of all, the first one, probably I should just think about addition, right? Addition of vectors. That's how I'm going to upgrade this. And this I can think about a statement about norms. In one variable, this was absolute value. In higher dimensions, in infinite dimensions, whatever, this should be a norm. This is slightly more complicated, because if you're thinking about the product of two numbers, in higher dimensions, you can generalize it in two ways. You can say, oh, like your colleague suggested, This one actually is a scalar. This one is a vector. So this would generalize to scalar multiplication. Or you could say, actually both of these are vectors, but how do you multiply vectors to get a number at the very least? Well, that's an inner product. Okay. Same statements hold for these ideas. So this now generalizes to vector addition. This generalizes to scalar multiplication and inner products. And this generalizes to norms. When I gave you that exercise, go back to your 3210 lecture notes or textbook, rewrite what they said to you. I mean something like this. In fact, you can say, you can put minus y sub n here. And again, that would give a statement. Let me not write that. And that would generalize to distances in here, or distances. Okay. This is leading to that exercise that I gave at the end of last class. And I should also mention, just as you can go back to your single variable notes and sort of reinterpret everything in terms of higher variables, if you're getting stuck in higher variables, you can also go backwards and say, okay, I'm confused about vectors, whatever, function spaces, all that stuff. Let me just pretend everything is a number. Get something, get some idea. Of course, there are certain traps there that you need to be careful about. But it's still a very good thing, very useful, I think. And so based on these, here's this exercise that I mentioned last time again. And I think I'm going to do at least one of the parts. So let's start like this. Let x, let's say xd, be a metric space. And so when I write it like this, this is sort of like the more formal statement, because a metric space, when you think about it, is a pair where the first entry is a set, the second entry is a function, a certain function satisfying certain axioms. Then D, it's a function. Is continuous. Now, what is going on here? X is a metric space. This X is also a metric space. And we talked about how you can think of the product of two metric spaces as a metric space in and of itself. So this too, this X times X itself is a metric space. So D is a function from one metric space to another. And here, of course, reals, or a subset of reals, is a metric space by the standard Euclidean norm, which is the absolute value of the difference of numbers. Okay. Now you can use the epsilon delta stuff here, or epsilon n stuff here, but this exercise that I gave you last time perhaps is even easier. That is to say, using sequences perhaps is easier. So what does this require? So instead of exercise, let me perhaps say claim. By the exercise, from last time, it suffices to show, well, what do I need? I'm going to take two sequences, one for this argument and one for this argument. Both converge to some points. And then I want to look at the distances between the nth terms. And I want that sequence of distances to converge to the real number that is the difference, that is the distance between the limits. In other words, if x bullet converges to x infinity and y bullet converges to y infinity, then I want this. Limit as n goes to infinity of d of x sub n y sub n equals d of x infinity y infinity. So I have two signals. They both converge somewhere. And I look at the distance between the corresponding terms. I want those distances to converge to the appropriate value also. Does this make sense so far? This is an important part. A big problem in this class is going to be, okay, so I have this complicated statement. How do I rewrite it in such a way that I have an actionable thing? This is rather more actionable because this already tells me, okay, so if I fix these two things, now this is a sequence of real numbers, and I can sort of try doing something with sequences of real numbers, you see. Questions? Okay, now how do you show this? Well, this sequence of real numbers converges to this if and only if, of course, the absolute value of their differences goes to 0. Okay, that's the distance in this space, really, but so I have something that I need to bound by epsilon for arbitrarily small epsilon. So once, now that I fixed my signals, x bullet and y bullet, and the targets, x infinity and y infinity, I have this sequence of numbers and this number. Goes to 0 as n goes to infinity. And how do you show things like this when you're trying to make sure that a sequence of numbers converges to 0? Well, you often bound it by something that you know for sure goes to 0. Right? That's pretty much the only way. Okay. Well, what can we use? The only thing we have is that D is a metric space, which pretty much means that the only thing I know is, again, that D satisfies the triangular inequality. And so what I can do is something like this. This is what I'm trying to bound. Let me subtract and add. Let's say D of x sub n against y infinity. I just added and subtracted the same number. How did I know that I had to, this would have worked? Well, we haven't seen it yet, but we're going to see in a second it does work. Well, this is sort of like one of the common tricks. Ultimately, it's experience, but the point is that you sort of, when you have two variables here and two variables here, and if you're trying to bound them, you sort of do the crisscross, and somehow things cancel out and stuff. That's the general trick. So I'm trying to bound this. This is the same thing as that. Of course, I can apply the triangular inequality. So this is one number, and then this is one number. I'm looking at the sum of two things. Or if you want, I can put here a minus and collect the terms. Like so. I have one number minus another number in absolute value. Applying the triangular inequality with absolute values. And that this is bounded by this. Minus, oh, there's a minus here. So let me put it like this, x infinity minus dxn y infinity. Oop. Oop. Now what? Now we can use something that we learned last time. We proved a statement where we can use here. How can I bound this? I don't have an inner product. We proved one thing about triangular, or about metric spaces so far. Look at your notes. Triangular inequality is in the name. Yeah, reverse triangular inequality. What does that say? It says that this is bounded by d of yn y infinity plus this is bounded by d of xn x infinity. But yn converges to y infinity, which means that this goes to 0. So does this. Okay. So here I used triangular inequality, and here I used reverse triangular inequality. Okay. Now, analysis is hard in the following sense. When someone else does the estimates and stuff, everything is fine. But then when you see it out in the wild, it becomes harder to do the estimates yourself. So it is very important to sort of practice a lot of these ideas. Any questions about this proof? Are we again all clear that continuity of this d function, in a sense, continuity of d with respect to itself, if you want, is equivalent to this statement? Are we okay with this? No? Okay. But you're happy once I do this translation? Okay. So I want to focus on this. How do I go from the statement that d, this specific function, is continuous, to the statement that it is equivalent to showing this? I use this exercise, but let's try to unpack this a little bit. So whenever you see a statement like whatever blah, blah, blah function is continuous, you should immediately think about what is the input space. Can I think of it as a metric space? Metric spaces are where we talk about continuity. What is the output space? Can I think about metrics? So what is the metric here? And so I could say this product metric, okay, x, y, this is one element here, and then let's say x bar, y bar. We defined a bunch of metrics here, but how do you measure the distance between this point to this point? Well, you look at the distance between these two, they're in x, and let's say you add the distance between these two. Okay. And what is the metric here? Well, it's just, you don't write it like this, but if I have two numbers, what is the distance between them? A minus b in absolute value. Okay. And so what do I need to show that this function that goes from this metric space to this metric space is continuous? All I need to do is I need to verify that this function preserves convergent sequences. If a sequence converges here, the image of that sequence under this function should converge here. Okay. What is a convergent sequence in this product? Well, it's a pair of convergent sequences in X. Okay. So D is continuous. It preserves convergent sequences. Let's say it preserves convergence. So if you plug in a convergent sequence, the output should be a convergent sequence also. So you have your signal in your input space. You say, I have a nice summary for it. And then you apply your transformation. You say that that transformation, that function is continuous insofar as the output signal converges to the output summary. Okay. And what is a convergent sequence? And so in x times x, a typical sequence is of the form, well, x bullet, comma, y bullet. One sequence for the first component, one sequence for the second component, and these sequences are supposed to come from the original space X itself. I had two signals in my original space X, and I paired them. Okay, that's what I'm doing. Okay. This guy converges to this. This convergence now is relative to the metric on x times x. Okay? This is now a sort of double signal, if you want. In other words, it's a single signal in x times x. Okay? And so is this. So this is just one point in x times x. But what does it mean for this guy to converge to this? Well, I look at the metric. This is my metric. Okay? Now, I need to use that metric over here, so let me write it like so. X sub n, comma, y sub n, x sub infinity, comma, y sub infinity. I want this limit to go to 0. But what does that mean? Open this up. This means this. Okay. By the definition of d sub x times x. I just opened the definition. But I assumed, well, I guess one needs to show this first, perhaps. This is where I sort of became a little bit loose, perhaps. From here, I immediately said that this is equivalent to saying the xn x infinity is 0, and so the fact that this statement implies this is a limit law for a sequence of real numbers. How do you go backwards? Well, I'll leave that to you, actually. It's a nice exercise. Certainly, it is believable. One thing you can say is that both this and this are sequences of real numbers that are bounded from below by 0 by hypothesis, because these are supposed to be distances, and distances are supposed to be non-negative numbers. Well, if the sum of two things converge to 0, and if neither of these take negative values, there could be no cancellation, which means that the only way this can happen is both of these components go to 0. That's one way of stating this. And once I have this, of course, what is this? This means that x bullet converges to x infinity, and this means that y bullet converges to y infinity. Okay. Does this make sense? So here, by the exercise, it suffices to show. We verified that it suffices. Or maybe we should start here. Why is it the case that it suffices? Questions or comments about this? Now we're building up more and more structures, and as you can see, there's going to be a whole sort of the princesses in another castle phenomenon here. You're just going to have to keep opening up the definitions and stuff. But once you get used to these ideas, you'll be able to sort of compress them again and sort of use them much more conveniently. This is a very important idea. This self-referentiality is a very important idea as well, the content of the claim. Now that I said this, and we're running out of time, I'm not going to write it again. I just want you to look at the sum of two numbers converging, or sequences of numbers converging, or the norm converging, all of these. I want you to reinterpret everything, all of those statements, in terms of convergence in metric spaces, and prove them again. There are, again, tricks involved, like the trick that I erased. You sort of add and subtract the cross terms. These are very good exercises. OK, that's a good place to stop. Thank you. I'll see you on Monday.